Good afternoon, students. In this lecture of quantum mechanics, we will discuss another application of Schrodinger's equation, that is motion of a particle in a 3D box. Now, in the last two lectures I have already discussed with you motion of a particle in a 1D box. So, today we will talk about the particle in a 3D box. So, now as you can see, the dimension of this box is A, B and C as is seen in this diagram, and the particle is confined inside the box. The particle does not lie outside the box, and inside the box there is no force acting on the particle, and the potential energy in this case is independent of time and it is zero within the box. For these limits of x, y and z, the potential energy is zero, and the potential energy is infinite elsewhere, that is at the boundaries and outside the box the potential energy is infinite. So since the particle exists only within the box, so therefore the wave function has its existence only inside the box and the wave function is zero at the boundaries and elsewhere. So now we have to solve the Schrodinger's equation and find out the wave function for such a particle. So first we will solve the time independent Schrodinger equation to get the psi. So since there is a motion in 3 dimensions, so I write down the time independent Schrodinger's equation in 3 dimensions. So this is the time independent Schrodinger's equation in 3 dimensions. Now inside the box, as I said, the potential is 0. So this equation reduces to this form. Minus h cut square by 2m. M is the mass of the particle. Grad square psi is equal to E psi, where E is a constant. It indicates here the energy of the particle. So now I'll just write down this equation. So if this equation will take the form, so here psi is a function of x, y, z. Yes. So 2me by h cut square is a constant here. Now this grad square psi we will write it as del 2 psi del x square plus del 2 psi del y square. Yes, we are writing down this grad square psi in Cartesian coordinates. As we have drawn the box in terms of the Cartesian coordinates equal to 0. So if you just compare with your 1D equation, there psi was a function of x only. So you had only this term plus this constant into psi equal to 0. But now psi is a function of x, y, z. So you have the dependence of psi on x, you have y and z. So you have the second order derivatives in terms of x, y and z. So to solve this equation, now again we have to separate out these variables x, y and z. So we will be using the method of separation of variables once again to solve this equation. So what I do is, so just like the method we followed when we have found out the time independent equation from the time dependent one, we will assume that let psi x, y, z be equal to some function of x. So this capital X is a function of this x into some function of y into some function of z. Okay. Now what we will do, if I say that this is a solution of this equation, so that means this satisfies this equation. So I have to find out this second order, the differentiations of these terms, and I just have to put it over here. So if you find out del 2 psi del x square, that will be simply d2x dx square into yz. Do you all agree to this? Because this here I write del because here psi has dependence on x, y and z. So I just take the partial derivative of psi with respect to x. But capital X is solely dependent on small x, so I write it as a total derivative. And this y and z, they are functions of small y and small z, so they will not contribute anything to this differentiation when I differentiate with respect to x. So these remain unchanged into d2x dx square. So this can be written as say x double prime yz. Double prime here indicates this double differentiation. So similarly, this del 2 xi del y square will be equal to x y double prime z, and del 2 xi del z square will be equal to x y z double prime. So now what we will do, we will just put these expressions back in this equation, and in place of xi we will put x y z and see how it looks like. So if I just put it over here, so it will look like this: x double prime yz plus x y double prime z plus x y z double prime plus 2me by h cut square into x y z is equal to 0. In place of xi I put x y z. Now the common trick is we want to separate the x, y and z terms. So we will divide this equation throughout by this product of these three functions x, y, z. So if you divide it, now the equation will look like this: 1 by x d2x dx square. X double prime I just write it as d2x dx square plus 1 by y d2y dy square plus 1 by z d2 capital Z d small z square plus 2me by h cut square equal to 0. This is how it will look like. Now let us just take a look at this E. This E is the energy of the particle. Now since the potential energy of the particle here is 0, so this E indicates the kinetic energy of the particle. Okay. So since the particle here is moving in all three directions, x, y and z direction, so if v is the velocity of the particle, we can actually write down the components of this velocity separately in x, y and z direction as vx, vy and vz. Okay. So the energy will be the sum of the kinetic energy along the x direction plus y direction plus z direction. That will be the total kinetic energy, and that is equal to this energy E of the particle since the potential energy is 0. So this will be half m vx square plus half m vy square plus half m vz square. This is how it will look like. So I can write this as, say, ex plus ey plus ez. So kinetic energy in x direction plus kinetic energy in y direction plus kinetic energy in z direction. Okay. Now these, mind it that these are all constants because the total energy E is a constant. So these are all constants. I just write here this x, y, z to indicate that I am indicating these constants in the for the three separate directions x, y and z. So now I will replace this E as ex plus ey plus ez and rewrite the equation. So here I am just replacing E by ex plus ey and ez. So plus 2m ex plus ey plus ez. So therefore now I can separate this entire, or I can write down this equation as sum of a function of x plus a function of y plus a function of z. So let me just rewrite this equation as 1 by x d2x dx square plus 2m ex by h cut square plus 1 by y d2y dy square plus 2m ey by h cut square plus 1 by z d2z d small z square plus 2m ez by h cut square. So the third term is this 1 by z d2 capital Z dz square plus 2m ez by h cut square equal to 0. So this is a function of x, this is a function of y, and this is a function of z. This is constant, constant and constant. Okay. So a function of x plus a function of y plus a function of z can be equal to 0 only if each of the three functions are separately equal to 0. So from here, now we can write down the three equations separately. One depending on x only. So I can write this constant as, or let me just write it as plus k square x equal to 0. So another equation is d2y dy square plus k, so let me name it as k1 square, k2 square y equal to 0. And the other equation that I get is the third equation. So I get now three separate equations. One depending solely on x, another depending on y, another depending on z. So this problem that we had in the beginning, that the equation was psi was dependent on x, y, z, and the equation had terms containing all the three variables x, y, and z. Now we have separated into three different equations, one depending on x, one on y, one on z. So now we can write down the solution of these three equations. Now these three equations are exactly the same equation that you got. They look like the same equation that you got for a particle in a 1D box. For particle in a 1D box, you got one equation only. And now for a 3D box, you have three such equations. So now I will just write down the solution of this equation, because that already we have done when we discussed for a particle in a 1D box. So this solution, we know it looks like a sine k1x plus b cos k1x, right? Similarly from here, so this is the solution of this. Now this y solutions are, it will look like, say, c sine k2x plus d cos k2x, and this equation capital Z will be, say, g sine k3x plus h cos k3, sorry, this is y, this I am solving in terms of y, and this is z, right? So we have got three solutions, x as a function of x, this is a function of y, this as a function of z, and we have two constants in each case. Okay, so now we have to apply the boundary conditions to find out these constants. Now see, once you have solved it for the 1D case, now for the 3D case is just a replica of that we are doing. For the 1D case, you had only one such solution because it was dependent only on x, and we put the boundary condition, we found the value of a and b. Now for the 3D case, you will be applying the boundary conditions for x, for y, as well as for z, but the results will be similar. So what will the boundary conditions here look like? So psi here is a function of x, y, and z, right? And this and psi, we know it is 0 at the boundaries. Okay, so from there I can say that this psi I have taken is a product of x, y, z, these three functions. So if psi is 0 at the boundaries, that is at x equal to 0, y equal to 0, z equal to 0, and at x equal to a, y equal to b, and z equal to c, psi is 0. So I can write that separately these functions, x is equal to 0 at x equal to a, and x equal to, sorry, at x equal to 0 and x equal to a. Similarly, I can say that this function y is 0 at the coordinate y equal to 0 and y equal to b, and z is 0 at z equal to 0 and z equal to c. So these are the boundary conditions. So if we apply this first boundary condition here to this, so x is 0 at x equal to 0 and x equal to a. So when x is 0 at x equal to 0, already we have done this for the 1D case, we will get that the constant, so x equal to 0 at x equal to 0 will give the constant b to be 0. So x will be a sine k1 x. Okay, now we will apply the next boundary condition, that x equal to 0 at x equal to a. a. So from here we will get that 0 is equal to a sine k1x. So a cannot be 0, then this function will be 0, and if this is 0, psi turns out to be 0. So sine k1x is 0. So the values of k1x will be, say, n1 pi, where n1 is a constant having values 1, 2, 3, 4. It is an integer. So k1 is n1 pi by x. So from there, the solution of x that we will get is that this k1 here will be replaced by n1 pi by, n1 pi by, this is a, n1 pi by a into x. Okay, so this is what we have got by applying this boundary condition, that capital X looks like a sine n1 pi by a x. So actually here this is a. Okay. So similarly, now applying this boundary condition, this y, in this y, this d will be 0, okay, and c will be non-zero, and y will look like k2 will be n2 pi by b. So n2 pi by b into y. Similarly, in z, I have to apply this boundary condition, and here z equal to 0, as z equal to 0, this will give me h to be 0, okay, and the next boundary condition, z equal to 0 as z equal to c, will give the value of k3 as n3 pi by c. So this will be n3 pi by c into z. Okay, so by applying the boundary conditions, we have got the function x, y, z to look like this. X is a sine n1 pi by ax, y is c sine n2 pi by by, and z is g sine n3 pi by cz. Now how to find these constants a, c and g? We have found this out from the normalization condition for a 1D case. For the 1D case, we found out this a from the normalization condition. So here also we will be doing the same thing. So if I apply the boundary condition, the normalization condition, that 0 to a mod x squared dx is equal to 1, because the limit of x is from 0 to a. So from here I will get that a square sine square n1 pi by ax is equal to 1, 0 to a, and this will give me a is equal to root 2 by a. I am not working it out because it's the same integration which we have done in our earlier lecture. So now x will look like, root 2 by a sine n1 pi by a x. Similarly, if I apply the normalization condition for this, that 0 to b mod y square dy is equal to 1. If I apply this, this will give me the constant c as root 2 by b. Okay, so here I will just replace this by root 2 by b, and for this again I will apply 0 to c integral mod z square dz is equal to 1. This will give me g is equal to root 2 by c. So I will replace here this g by root 2 by c. So I will replace g by root 2 by c. So x looks like this, y is this, and z is this. So we have solved the time independent Schrodinger equation. So now my psi x, y, z will look like 2 root 2, because it's a product of x, y, z, by root over of a, b, c sine n1 pi by ax sine n2 pi by by sine n3 pi by cz, where this n1, n2, n3, they all are constants and have values starting from 1, 2, 3, because none of them can be 0. Any one 0 turns out this function to be 0. So the minimum value of n1, n2, n3 has to start with 1, 1, 2, 3, 4 and so on. So this is how, so this is a solution of the time independent Schrodinger equation. And what about the energy eigenvalues? So the energy eigenvalues, so we will just write down the energy eigenvalues from here. Or I think I will stop here with the energy eigenvalues. We will discuss in the next class. I will just write down the expression and I will discuss it elaborately in the next class. So E here will be, as I said, it was Ex plus Ey plus Ez. So Ex is, so we have written 2m Ex by h cut square is equal to k1 square. Okay. Now k1 we have got is n1 pi by a. So n1 square pi square by a square. Okay. So from here therefore we get that this Ex is equal to n1 square pi square h cut square by 2m a square. This is the type of result we got for the 1D case where the box was of length L. We got the same thing. Here there we wrote n square pi square h cut square by 2m L square. Here I got n1 square, and this for the x side the dimension is a, so I get it. So similarly I can write 2m Ey by h cut square is equal to k2 square and put the value of k2 square there. I will get the value of Ey and Ez. They will all look, they will all have a similarity with their expression. So I will just write it in 1 square pi. So pi square h cut square by 2m is a common term that you will get once you add those three. So you have n1 square by a square plus n2 square by b square plus n3 square by c square. So this is how your energy eigenvalues look here. Okay. So these are the energy eigenvalues, and this is how the time independent Schrodinger equation solution, the Xi xyz looks like. Now in the next lecture I will discuss with you this solution as well as these energy eigenvalues in details. Thank you.